Hello everyone, in this video we will continue talking about Newton-Raphson method in n dimensions. We will talk about the halting condition for Newton-Raphson method, and also I will show you an example about how to use this method to find the root of a system of equations. The halting condition for the Newton-Raphson method in n dimensions. So it's very similar to the halting condition for Newton-Raphson method for a scalar valued function. So there are three different conditions which may cause the iteration process to halt. First, we halt if both of the following conditions are met. Condition A is that the step between successive iterates is sufficiently small, and which means that the norm of the vector xn plus 1 minus xn is less than a constant, and this constant is epsilon step. And the condition B is that the function evaluated at this point, xn plus 1, is sufficiently small, which means the norm of f xn plus 1 is less than a constant, and this constant is epsilon abs. So the only difference between this halting condition and the halting condition we used for Newton-Raphson method for scalar valued function is that the absolute value here is changed to norm, and this norm can be 1 norm, 2 norm, or infinity norm. Later in this class, I will show you how to calculate norms, different type of norms for vector and also for matrix. The second halting condition, if the Jacobian is invertible, that is the determinant of Jacobian matrix is 0, then the iteration process fails and we halt. So this is similar to the division by 0 problem in the halting condition for scalar valued function. The third halting condition, if we have iterated some maximum number of times, say n, and haven't met condition 1, and then we halt and indicate that a solution wasn't found. And if we halt due to condition 1, we state that the vector xn plus 1 is our approximation to the root. And if we halt due to either condition 2 or condition 3, we may either choose a different initial approximation or state that a solution may not exist. All right, so for Newton-Raphson method in n dimensions, you don't need to know how to implement this method in MATLAB. So I will just show you an example about how to use this method to find the root of a system of two equations by using hand calculation. All right, so this problem is a problem on the textbook. It's 12.8. Determine the solution of simultaneous nonlinear equations. The first one is y equal to negative x squared plus x plus 0.5. And the second equation is that y plus 5xy equal to x squared. And use the Newton-Raphson method and use the initial guess x equal to y and equal to 1.2. So let's do the first two iterations. Just for demonstration, we do first two iteration. All right. So let's first see what's the function f1. So remember we have a system of equations f1, which is the variable is x1, x2 until xn equal to 0, right? And f2, which has x1, x2 till xn equal to 0. So we first need to change the two equations in the form that x1 equal to 0 and f2 equal to 0. So f1 here, we can assume it's y plus x squared minus x minus 0.5 equal to 0. Just move everything to the left-hand side and make the right-hand side equal to 0. All right, so similarly, f2 will be y plus 5xy minus x squared equal to 0. All right. And when we do the first iteration, we need to evaluate the Jacobian inverse at the point x0, y0, right? So here x0 equal to y0 equal to 1.2. And all right, so when we find the Jacobian inverse, there is actually a formula for 2 by 2 matrix. Assume matrix A is A, for example, it's A, B, C, D. It's a 2 by 2 matrix. The inverse of matrix A actually equal to the matrix D minus B minus C and A over a constant, and this constant is the determinant of A. Okay, so use this formula, we can find Jacobian inverse, and then we can assess the value of a Jacobian inverse at the point x0 and y0. All right, so let's do the first iteration. The formula is x1, y1 equal to x0, y0 minus Jacobian inverse evaluated at x0, y0 times the function value evaluated at x0, y0. So this is f1, x0, y0, and this is f2, x0, y0, right? And so let's see f1. Actually, f1, x0, y0 equal to, we just need to plug in 1.2 into this equation for f1, right? All right, so it's 1 point, so let's use MATLAB as a calculus. So it should be 1.2 plus 1.2 squared minus 1.2 minus 0.5, right? So this is 0.94. So this is 0.94. So let's evaluate f2 at x0, y0. So f2 is actually this equation, y plus 5xy minus x squared. So y plus 5 times xy minus 1.2 squared. So this should be 6.96. So this is 6.96. Then we evaluate the Jacobian, okay? So Jacobian, let's first see what's the Jacobian. So Jacobian is f partial derivative of f1 over the partial derivative of x, right? So this will be 2x minus 1. And the second term will be the partial derivative of f1 about y. So this will be 1. And the second line, the first item, will be the partial derivative of f2 about x, which is 5y minus 2x. 5y minus 2x. And then partial derivative of f2 about y, so which is 1 plus 5x. And then we can find the determinant of Jacobian. So this will be 2x minus 1 times 1 plus 5x minus 5y minus 2x. All right. So the Jacobian matrix, the inverse, will be equal to, so let's see the formula. So it's D minus B minus C and A. So D, which is 1 plus 5x, minus B minus C in A. All right, over the determinant. So this determinant, if you write up, is 10x squared minus 3x and minus 1 minus 5y plus 2x. So it's 10x squared minus x minus 5y minus 1. All right, so this will be the denominator. All right, so this is Jacobian inverse. So we need to evaluate the Jacobian inverse at the point x0, y0. Right, so this will give you a 2x2 matrix. So let's see what's this. Let's first see the denominator, 10x squared minus, so because x equal to y in this case, so 10x squared minus 6x minus 1, okay? So 10x squared minus 6 times x minus 1. So this will be 6.2. Right, so this will be 6.2, and so it's 1 plus 5 times 1.2, so it's 7. This is negative 1, and here it's negative 3.6. All right, so this is 3.6, and this is 1.2 times 1.4, all right? Okay, so this will be the Jacobian inverse, and we need to write the formula here. So right now we have got this function value evaluated at this point. We also got the Jacobian inverse evaluated at this point. We just need to put them into this formula, right? Okay, so let's see. So it's still the first iteration. We have x1, y1 equal to x0, y0 minus the Jacobian inverse evaluated at this point. It's 7, negative 1, 3.6, 1.4 times the function value, which is 0.94 and 6.96. Okay, so you need to evaluate. This is 1.2 minus, and this value is, so let's assume this is equal to a 2x1 vector. So the first vector will be, the denominator is still this one, and it is equal to this one times this vector, right? So it's 7 times 0.94 minus 1 times 6.96 and divided by 6.2, right? And the second element will be this vector times this vector. So it's negative 3.6 times 0.94 plus 1.4 times 6.96 over 6.2. Okay, then you can calculate this. So I will show you directly that the result will be 1.26 and 61, and here it's 0.174. So this is the result for the first iteration. So let's see the second iteration. The second iteration, the formula will be x2, y2 equal to x1, y1. We just got x1, y1 from the first iteration, right? So minus Jacobian evaluated at x1, y1, Jacobian inverse actually, and then the function value f1 and f2 evaluated at x1, y1. All right, so first we need to evaluate the function at this point. So the function will be, so f1, x1, y1. We want to evaluate f2, x1, y1, right? So f1 is y plus x squared minus x. So let's see, x is equal to 1.61 and y is equal to 0.174. So the x1 is y plus x squared minus x minus 1/2. So this will be 0.003. So this is 0.003. And the f2 will be y minus x squared plus 5 times x times y. So this will be negative 0.319. Negative 0.319, right? And then we need to evaluate the Jacobian inverse. So we already got the Jacobian inverse. Looks like this. So it's 1 plus 5x negative 1, 2x minus 5y, 2x minus 1 over 10x squared minus x minus 5y minus 1, right? So this will be, let's first evaluate the denominator, 10x squared minus x. 10 times x squared minus x minus 5y minus 1. So this will be 12.77. So let's see the matrix. It's 1 plus 5 times x in 2 times x minus 5 times y. Also the 2 times x minus 1, right? Okay, so we got the Jacobian. So this is 7.305. This is 1.652. This is 1.522. Okay, so then we can use those values we got, plug into this formula to get x2, y2. Okay, so still the second iteration. So we get x2, y2 equal to x1, y1, which is 1.261, 0.174 minus the Jacobian inverse evaluated at x1, y1. So this will be the matrix 7.305, negative 1, 1.652, 1.522 times the vector 0.003 and negative 0.319. All right, so you can multiply so this 2 by 2 matrix times the 2 by 1 vector will be a 2 by 1 vector, so we can write it up. So the first element will be this vector times this vector. So it's 7.305 times 0.003 plus 1 times 0.319. Right, so also divided by 12.77, and the second one will be this vector times this vector and then divided by 12.77. So it's 1.652 times 0.003 and then minus 1.522 times 0.319 over 12.77. All right, so the result will be this one minus this one, right, and this one minus this one. So the result is actually x2 equal to 1.234 and y2 will be 0.212. Okay, so for this method you don't need to know how to implement it in MATLAB. So in the next video I will talk about the quiz problem.